Hey students, in this video we're going to go over entropy. So first off, I want to talk about this idea of a spontaneous process. So a spontaneous process, or rather, we try to use the phrase thermodynamically favorable. Okay, I know that's a mouthful, but thermodynamically favorable. Let me write that down here. It's the same thing as spontaneous process. It just means that once the reaction starts, it's going to keep going without any outside intervention, thermodynamically favorable. We try to use this phrase because that's the way that the AP testers are trying to go towards, and using that phrase thermodynamically favorable rather than spontaneous process. Now you will hear me say spontaneous process though, just because it's been ingrained in my head and I'm trying to use the new terminology. Anyways, so with spontaneous, or rather thermodynamically favorable processes, it favors the formation of the products rather than the formation of the reactants. And it's going to, like I said, once the reaction starts or the process starts, it's going to keep going without any outside intervention. Some processes happen quickly, some processes happen more slowly, like this picture of the ice melting. Okay, it's going to start and it's going to keep going without any outside intervention, but it's a slow-going process. Okay, so spontaneous process, thermodynamically favorable processes doesn't talk about how quickly it happens. It will happen without any help. Okay, so we're going to talk about this idea of entropy. And entropy is the amount of disorder in a system. And the world kind of tends towards and leans towards disorder rather than order. I know me personally, I'm a very disordered person. If you were to look at my desk, there's papers everywhere. It's very rarely ever clean. It just so happens that things like piles of paper end up here and here and here. There's calculators everywhere, dry erase markers everywhere. It just happens. It's a very natural process, this idea of disorder. Okay, it takes work to be order. Okay. So anyways, that's what entropy means, disorder. So the higher the entropy, the more disordered the system. The lower the entropy, the more ordered it is. So when we're looking at thermodynamics and we're talking about those thermodynamically favorable processes, they always lean towards an increase of entropy. And that's because, like I was saying, it's much more common to have something that's disordered than something that is ordered. Like if you're this guy down here in this picture and you're throwing these bricks, the chances of them landing in this nice, neat, ordered stack is very, very, very low. But there's so many different possibilities for these bricks to end up in a messy, haphazard, random, ordered stack, okay? So entropy is always increasing in those spontaneous processes. As far as we're talking about in chemistry and our chemical reactions, there's different things that we can look at in order to determine qualitatively whether or not the entropy is increasing in a system. So first off, we can look at the states of matter. So entropy increases going from a solid to a liquid to a gas. And in this picture here, you can easily see why that's the case. When you look at solids, solids have particles that are really tightly packed together and they're very ordered. So they're going to have a very low entropy. But gases have fast moving particles, they're far apart, they're constantly moving. And so gases are very disordered. The next case is that entropy increases when solutions are formed. So when things are formed in solutions, let's talk about ionic compounds, for example. When ionic compounds dissolve in solutions, the water breaks apart salt, for example, NaCl, into its two ions, Na plus and Cl minus. When sugar dissolves in water, you're going from a solid structure of sugar and you're pulling those molecules away from each other. And that's why it's more ordered, or sorry, more disordered, higher entropy when the solution is formed. Entropy increases in a reaction when more atoms or molecules are formed. So you can look at an overall reaction, you can look at your coefficients to help you determine whether or not you're going to a higher entropy or a lower entropy in the formation of the products. And then lastly, entropy is going to increase with temperature. We know from previous units that as the temperature increases, the molecules are moving more, and more movement leads to more disorder. So here's just a couple of ideas here about entropy, okay? So it says that the change in entropy tends to be positive, and positive means more disorder when the reaction is exothermic, and that's because we know that exothermic reactions release heat energy. So if it's releasing heat energy, there's an increase in temperature, which we just talked about. Increase in temperature increases entropy. And then the spontaneous processes happen when entropy increases. So when you're going towards those gases, or when you're making more, products than you have in your reactants, it tends to have a positive entropy. Now we will be calculating the change in entropy just the way we calculated the change in enthalpy. When we do quantitative entropy calculations, we're going to take the sum entropy of our products minus the sum of the entropy of our reactants. And we'll use that same chart from before on pages 4 and 5 in our packet to look up the entropy values. So you'll be using the column with the S on the top when you're trying to calculate the change in entropy. So we're going to predict the sign of entropy for these different processes here. Now again, positive means that it's going to be more disorder. A negative entropy would be less disorder or more order. So when you look at number 1 here, all of these are gas particles, so we can't use the state of matter there. So we can look at how many particles we're having from the reactant side to the product side. On the reactant side, we have 4 gas particles, 3 hydrogen, 1 nitrogen. On the product side, we only have 2. So we're getting more ordered, less disorder, so this is going to be a negative. On number 2, we have 2 solids on both sides of the reaction, but we have a gas on the reactant side. We don't have any gases on the product side. So again, this is going to be negative because we're getting more ordered, less disorder. On number 3, we have a solid and 6 gas particles on the reactant side. And on the product side, we have 12 gas particles. So we are getting more disordered. So this one is going to be positive. On number 4, you can see that we're going from a solid and we're going to form a solution. Aqueous means dissolved in water solution. So we're getting more disordered. So this one would also be positive. Number 5, silver chloride precipitating from solution. That's a keyword here, precipitating. That means we're forming a solid. So that means it's going to be negative entropy. Alcohol evaporating. Remember, evaporating means that we're going from a liquid to a gas. So since we're forming a gas, we're getting more disordered. So entropy would be positive. Solid iodine dissolves in carbon disulfide. Keyword here, dissolve. Dissolving when we form a solution, we're getting more positive entropy. And then when water cools from 35 degrees to 25 degrees, we're getting more ordered. So it's going to be negative entropy because the temperature is decreasing. Okay, so that's a qualitative way to assign entropy values, is to just look at the process or the reaction and make a determination on whether or not the entropy would be positive, more disorder, or if it would be negative, less disorder or more order. Now we can also look at reactions themselves and calculate quantitatively what that change in entropy would be. So let's go ahead and write our reaction first. We've got, I don't know why my computer just shut off. So sorry. We've got aqueous nitric acid, HNO3, aqueous, is neutralized with calcium hydroxide, aqueous. And it's a double replacement reaction, so we're making calcium nitrate. And that is going to be aqueous because it's a nitrate. And we're making water. liquid water. So let's go ahead and balance. So when you're looking up these values, sorry, my computer keeps turning off. We're going to start looking on page 4, and we're going to look at the S column, the entropy column. I know where water is. It's right up at the top. And so this is for liquid water. It's 69.95. I gave you calcium nitrate in here, so that's 193.2. Calcium hydroxide aqueous is going to be, it's not on page 4, so page 5. Calcium hydroxide, 76.1. And then nitric acid, it's over on the right side, aqueous, 146.4. Now remember, we need to multiply by our coefficients the same way we do when we are calculating the change in enthalpy. So 2 times 146.4. So this is 292.8. 2 times 69.95. This is 139.9. So when I calculate my change in entropy, I'm going to do my products, 193.2 plus 139.9 minus the sum of my reactants, so 292.8 plus 76.1. So I'll go ahead and calculate this. And I'm going to get negative 35.8. And these units are joules per moles Kelvin. And if you forget the units for those, they're on the top of the charts on pages 4 and 5. Okay, so that's our answer for our entropy here. So going to our next reaction, lead 2 chloride reacts with aluminum oxide. So we have PbCl2 reacting with aluminum oxide. It's a double replacement reaction, so we have to predict our products. So that's going to be PbO, which is a solid, and aluminum chloride, which is aqueous. And then we can go ahead and balance. There we go. So let's go ahead and look up our values here. So first off, aluminum oxide is going to be 50.92. And aluminum chloride is going to be 110.7. I'm going to multiply this one by 2. Lead 2 oxide, make sure you look at those Roman numerals here. Lead 2 oxide is going to be 68.7 times 3. And lead 2 chloride is going to be 136 times 3. So let's go ahead and see what this is. 3 times 136. Now you're more than welcome to try to do this all in the calculator all at the same time, but people do make a lot of mistakes, I will tell you. So be very careful. Always make sure you're putting this into your calculators as well to make sure you're getting the same answer as me as you go. And to check my work too, because sometimes I do make mistakes. Now remember, when we calculate our delta S, we're going to do our products, 206.1 plus 221.4 minus our reactants, 408 and 50.92. So we should get plus 221.4, oopsie, 408, 50.92, negative 31.42. And that should be our answer for our delta S here. So if you have any questions about calculating your delta S or being able to predict whether or not a process is going to be a positive entropy or a negative entropy, just let me know. Thanks.